Hello, I'm Sophia, and today I'm going to talk about delocalized electrons. To understand delocalized electrons, we first need to understand what a pi bond is. And to understand what a pi bond is, we need to understand what a sigma bond is. A sigma bond is a single bond, or it's a head-on overlap of hybridized, that means mixed, s and p orbitals. So you can see on this picture with the ethylene molecule that you have a carbon-hydrogen. And these carbon-hydrogen bonds are formed by an sp2s overlap. Now, the important thing is you might think, what is an sp2 overlap? It's simple. It's one s orbital and then two p orbitals to kind of concentrate into one orbital like this. And then s, so in complete, the orbital looks a little more like this. However, with the carbon-carbon bond, you see it's formed by sp2 overlap and then another sp2 overlap. That shows that the carbon-carbon bond is in fact a double bond and that there are pi bonds. You can see that the sigma bond is right on the plane of the carbon-carbon bond. So the pi bonds are forced to be above and below the plane, since you have to have two pi orbitals for one double bond. If you fit them together, they lie perfectly. So you can see the pi bond here and the sigma bond on the plane. Pi bonds are also a side-to-side overlap of the parallel p orbitals. Now, what are delocalized electrons? Delocalized electrons are electrons that don't belong to a bond. These electrons have bonding characteristics, but they visit two atoms. Delocalized electrons can be represented in two ways, through partial bonds or mainly through resonance. And delocalized electrons are in pi bonds. So you can see here, there's this benzene molecule, and this benzene molecule is kind of important because you can see right here, there's single bonds alternating with double bonds. So these double bonds are the pi bonds where the delocalized electrons are in. So they're here, and they're here, and the single bonds are where the delocalized electrons can move to. And this is the foundation for resonance, which we'll talk about later. Now, essentially, delocalization of electrons, it means that the electrons are able to move around the molecule. The electrons are not fixed. I explained with benzene that you have these double bonds where the delocalized electrons are in. They usually hop to these single bonds that are right next to them. This is a very common practice for these molecules with delocalized electrons. And since the electrons are delocalized, the charge is delocalized as well. And since the charge is delocalized, the molecule is more stable, and this is important. Now, delocalized electrons are first part of resonance, and they're part of resonance in aromatic compounds. But what is resonance? Resonance is a way to describe bonding in some molecules or ions through several contributing structures or forms. All the contributing structures, when you put them all together, they make a resonance hybrid. Benzene, theoretically, it has two resonance structures. One of these resonance structures is this one, and then the other one is where you swap single bonds to double bonds like this. So you take these two bonds and then take this bond out and then replace them with the two double bonds, which requires moving of the hydrogen. And then there's enough for the double bond to go in place. But the problem is, you can't have two double bonds in place. That's not allowed because one hydrogen is left over. So this benzene, gets the single bond back, but where did the single bonds go? So the issue is you have to change the other double bond, not the one that just formed, into a single bond. And then you have to do the same thing, and then you have to put the hydrogen back on this and replace this with a single bond to be able to connect the two atoms together. And you have to do this 3 times because there's 3 of these bonds per molecule. Because you immediately see, so now you can actually put the hydrogen on this one, but then you notice there's again going to be 2 consecutive double bonds, and then that's why you have to form this whole thing 3 times around to be able to change the resonance structure. And it's kind of like exchange between the molecules, like between the electrons. Now, all the contributing structures together make a resonance hybrid. Another example for this resonance hybrid is a carbonate ion. And a carbonate ion, you can see, has 3 different resonance structures. And these 3 different resonance structures look the same at first glance. They have a double bonded oxygen and they have a carbon with 2 negative ions. And then you can see, if you look at it a little bit more carefully, then you notice that, well, if you look at the structure number 1, you get the first structure. So you if you look at structure number 1, you can see at the beginning, so you can see right here, here's the double bonded oxygen, here's the negatively bonded oxygen, here's the negatively bonded oxygen, versus here's the negatively bonded oxygen, here's the double bonded oxygen, and here's the negative and double bonded oxygen. Now, the way I represented resonance, so like rebuilding the molecule, kind of like swapping the bonds, isn't that right. The issue is because you can swap these bonds, but it turns out that these molecules aren't separate molecules, because if you need to swap the bonds, it kind of looks more like a separate molecule. These structures could be achieved merely through rotation of the molecule as well, in certain cases. And with the carbonate ion, that is in fact the case, but you kind of have to rebuild it when using your modeling. So you can't really do it using modeling, but you can do it the normal. So with Primero, you see right here, the carbonate ion. You see here's structure number 1. This is the first structure. And then 2 of the oxygen atoms merely rotate to be able to form the next structure. So you can see, and then that's true with the third structure because it can be rotated as well to form the third structure. So you can see it actually isn't. You don't need to rebuild all this. Now, we know that delocalized electrons are part of resonance, but they're part of resonance in aromatic compounds. And what are aromatic compounds? Well, they're those chemical compounds, most commonly organic, which contain one or more rings with pi electrons delocalized all the way around them. Remember that our benzene ring, when I showed the benzene ring on the other image, it kind of looked like this, except for the angles. Why? Because it didn't just show like the delocalized electrons. What it showed actually were a ring. And why did it show a ring? This is part of the reason why. So this is kind of like a more simplified way to show that these electrons are delocalized over the entire thing, like you saw in the modeling. Because in the modeling, you know the compound is delocalized over the whole thing because it has alternating single and double bonds, which makes it this delocalized mass. But they kind of represent it like a shorthand. But we'll learn more of the reason why this is a ring later on. Now, how do delocalized electrons take part in resonance and aromatic compounds? Now, aromatic compounds, like benzene, have a special property. They have a property of cyclic, that means ring-shaped, and planar, flat, structures with pi bonds in resonance, and those are the ones containing delocalized electrons, that gives increased stability compared to other geometric or connective arrangements with the same set of atoms. That's just other forms, for example, other resonance structures of the carbonate ion. And because of resonance energy, they're also stable from charge delocalization. So you can see here, there's a molecule called pyrrole. It's kind of benzene, except with one bond cut out. And then on the bond space, you have a nitrogen attached to a hydrogen instead. So you can see over here, you have this atom right here, these bonds, and you can see there are electrons all over the place here. And these electrons are delocalized electrons. They don't belong to any particular orbital. This is made by random chance. However, if you take the nitrogen and hydrogen attachment area and switch it up with oxygen to be able to do the sp2 orbital, it would still be able to migrate through this entire molecule, this arrangement through random chance. So you can see here, so you see this sp2 orbital, it can be moved. So it can be moved over the entire molecule. And you can see that with thiophene, when you replace the oxygen with the sulfur relative to furan, so you can see that the places where the delocalized electrons left, those are in the 2p orbital, and the ones where they stayed were in the 3p orbitals, but this is also random chance. Delocalized electrons are part of metallic bonding. And what is metallic bonding, first of all? It consists of cations in a sea of delocalized electrons, kind of like the one in benzene, but inside the molecule. That means that the electricity can move freely through the structure, can move all over the place, kind of. Metallic bonding enables electricity and electronics to work through transfer of charge, and it relies on the movement of these electrons. So you can see that there are a lot of cations in this picture, so right here. And then you can see these delocalized electrons on the top. And these delocalized electrons are the electrons that move all over the place. So they typically, these electrons move. This electron might move here, and this one might move here, and this one might move here. And because of all these movements, transfer of charge actually works. But they technically, most of the time, they move in a single direction, like this. We'll look at why later. Now, there are special properties of metals that are related to either metallic bonding or delocalized electrons. One of these special properties is called conductivity. Because the electrons can move freely all over the structure like this, if electrons would be pushed from a metal wire, they would move through the wire, so the electrons would move through the wire in a mostly, and not really random order, but kind of random. And then they would come out at the other end at the same rate. So if it's this rate, then it will come out of the other end at the same rate. Because conductivity is the movement of charge. And it's the same rate. You can see here. These electrons conduct electrical charge when a power source is plugged in. So you can see here there are copper atoms, and you saw immediately that a stream of electrons got moved like this. Whoosh, like that. And this is because you can see in the metal wire, they have to move in one direction to go to the end of the metal wire. You can see in the metal wire, most of the electrons are actually moving towards the end of the metal wire. They're kind of in semi-random directions going there, but if enough of these electrons go in one direction, like the end of a metal wire, then the charge movement is literally a stream of electrons, like this. Ooh, like that. There are other special properties of metals, and one of them is luster. So here in luster, the free electrons can absorb photons, so the metal looks opaque. However, thanks to luster, another thing can happen. The electrons can reflect light like this at the same frequency that light hits the material. So it's like this, so same frequency. So the metal doesn't look opaque. It technically looks silvery. So you can see here, this animation for luster. So you can see you hit this brick on the metal. And what happens is that the stream of electrons move away from each other. And then the metal kind of looks silvery due to the transferred electrons. Again, it looks like this. And you can see here that there's another special property, and that one is malleability. Because of malleability, a substance is not rigid, and its electrons can move all over the plane. That means all over the molecule, kind of. The reason that malleability is used in metals, so this why it's actually seen in metals, is because ionic bonding, on the other hand, has very rigid connections between protons and electrons. Very strong and rigid connections between a proton and an electron. However, metallic bonding is kind of in the middle of the spectrum because of another reason we'll talk about later. Metallic bonding allows protons to vibrate like this and electrons to move. That's why conductivity works. Because metallic bonding, due to its non-rigid connections, allows electrons to move and the protons to vibrate. Now, the last property is the metallic bonding in a solid versus the metallic bonding in a liquid versus in a gas. In a solid, actually, both the delocalized electrons, like in the benzene molecule here, delocalized electrons, and the interactions between them, in the case of the benzene molecule, the double bond, they're holding the structure together. In a liquid, only the electrons are keeping the structure from falling apart, so it can vibrate, kind of like this. However, in a gas, the elements can go anywhere, so I wouldn't need to, like, technically, if you break both of the bonds, and the electron can go anywhere, so all over the molecule, not even all over the molecule, all over the place, if it has sufficient energy. Now, the reason you can see is the Van Arco-Killar triangle. So the reason why all our bonding is kind of like it should be. Now, Van Arco-Killar triangles, they're triangles which are used for showing different compounds, like this one, in varying degrees of ionic, very rigid, metallic, kind of in the middle, and covalent, not rigid at all bonding. So chemical bonds are not particular bonds with a specific type. They're usually a blend. There might be a blend of 1 bond type, 2 bond types, 3 bond types. So you can see here, there's this first triangle where you can see that there's metallic bonds, covalent bonds, polar covalent bonds, and ionic bonds. So you can see from about 0.75 electronegativity to 2 electronegativity, everything is metallic. So it's kind of in the middle of the spectrum. Though the bonding is not very rigid, allowing protons to vibrate and electrons to move. Once you move to the very edge of the ionic bonding spectrum, you see that this bond is actually a mix. Well, it's a mix of both metallic, that means kind of rigid, and ionic bonding. But in this area, the amount of ionic bonding supersedes metallic bonding. Once you get to polar covalent bonds are a mix of ionic bonds and metallic bonds. So polar covalent bonds, so some of the polar covalent bonds at the edge of the metallic border they're a mix of ionic bonds, they're a mix of covalent bonds, and they're a mix of metallic bonds. The reason that this kind of works out like this is because you can see is because no ionic bond is fully ionic. They have some kind of covalent sharing here and there. Now, delocalized electrons are part of aromaticity, but we need to know conjugated systems first because generally a compound is aromatic only if it's conjugated. What is a conjugated system? It's a system of connected p orbitals with delocalized electrons in a molecule, which is conventionally represented as having a single and multiple bonds. If we look back at that benzene over here, you can see it has delocalized electrons and is commonly represented as having alternating single and multiple bonds. So single, double, through this 6-compound ring. And actually, in a conjugated system, multiple adjacent carbons must have p orbitals participating in pi bonding. You can see this one participates in pi bonding, this one participates in pi bonding, this one also participates, and this one participates, and this one participates, and this one participates. And you can see these bonds, they can be connected. They're kind of adjacent, and they can be connected through one single bond. So you can see that generally a compound is aromatic because it is cyclic and it's conjugated and it has 4n plus 2 pi electrons. That means that it must have this number of electrons for the molecule to have aromatic characteristics. It must also be flat, like this. So you can see in that benzene molecule, the benzene molecule has 6 p orbitals because it has 3 of these double bonds, and they give you 2 p orbitals each. Now, these things can be split. They can be split kind of not really evenly like this into one ring and then another ring. So one of the double bonds is kind of in the middle of the ring, and the other one is up the ring, and the other one is on the bottom of the ring, like this. And you can see because of that, the thing is delocalized. The molecule is delocalized. And you can see that the electrons can be swapped. This one moves here, this one moves, so this one moves here, this one moves here. And these are 2 resonance structures that kind of are in the middle, and that's why you have the ring, because these electrons can hop with the resonance structure. The electrons are delocalized over the entire molecule. Now, the aromatics, why is aromatics actually important? This is because they're stable. They're stable and they're non-reactive. And this is important for a variety of reasons. But a benzene, it needs to become another raw material to be processed. So you can't take this into an aromatics facility. It could be a few. It could be styrene, it could be cumene, it could be cyclohexene and alkobenzenes. Alkobenzenes because they're a whole group of compounds. Styrene has the formula C6H5CH-CH2. And it's used in automotives, it's used in computer housing, and it's used in insulation. Now, if you look at cumene, it's an organic compound that's based on an aromatic hydrocarbon like this one with an aliphatic substitution. It's used in CDs, it's used in safety helmets, and it's used in quote-unquote plastic glasses. So you can see cumene looks exactly like styrene, except that the double bond is out, and you can see these CH3 groups are on instead. And these groups, they're called methyl groups. But they show that it's a compound with an aliphatic substitution. So what is an aliphatic substitution? Simply, an aliphatic substitution is a substitution that attacks an electron-poor aromatic molecule like benzene, resulting in the substitution of a leaving group. So you can see our molecule looks almost like benzene, except that it has one nitrogen oxide over here and another nitrogen oxide over here. You can see the electrons can swap through resonance, and you can see there's this Nu nucleophile with an electron. And there's also a chlorine attached, which is a very good leaving group. So you can see the nucleophile needs to first move to the chlorine over here to be able to exchange its electron. So here its negative electron got moved first onto the nitrogen oxide. The nucleophile is here, and then the chlorine is here. You can see this arrow is the one pushing the chlorine out because it's supposed to be a leaving group. Then the nitrogen oxide electron moves over here through resonance swaps. It goes here and then here to be able to get to the chlorine, and the chlorine gets the negative electron, and you can see the chlorine has to leave. It's stable now because of the negative electron. Now, alkobenzenes are actually a whole group of compounds. They're benzenes with alkyl groups. And what are they used in? They're used in detergents and engine oil surfaces. You can see alkobenzenes are literally just benzenes, except you swap one of the hydrogens at the top, like this. So you swap one of the hydrogens on the top and put a carbon on top of it, and then from that carbon, put two diverging methyl groups. Then take a hydrogen on the bottom and then put a carbon and then put a methyl group on the carbon, like take a stem out of the carbon. Now, cyclohexane is a non-polar molecule with the molecular formula C6H12. It's used in auto parts, it's used in toys, and it's used in sports equipment. Now, cyclohexane is not that stable, but it has multiple forms. At this chair form that we're showing is a boat form, and a lot of different forms or structures. They're kind of the same molecules. So it's kind of like benzene's resonance structures, except the actual physical molecule's shape changes. Now, why is all this important? It's the foundation of resonance. The delocalized electrons, like for example in benzene, they're the foundation of resonance. If it wouldn't have been for these electrons, then the electrons would not be allowed to hop from here to here and then from here to here. And many molecules wouldn't form like with resonance, like benzene that we've used all the time. Benzene is a very significant contributor to the aromatics industry, and it relies on resonance to exist. Otherwise, there would be none of this. And benzene is the main raw material for cumene, styrene, alkobenzene, and cyclohexane. Styrene is used to make polystyrene and rubber products. Polystyrene is everywhere, whether in the home, office, supermarket, or even a fast food restaurant. Cumene, together with another compound, phenol, are used in many healthcare products, most notably aspirin and penicillin, one of the most used antibiotics. Cyclohexane is used as an intermediate to produce nylon because it's unstable. However, it's still important. Delocalized electrons have bonding characteristics. They're in pi orbitals, but are not bonding electrons because they can move. They can be represented through partial bonds, kind of 1.5 bonds, or resonance, which means that the molecule has several forms. Delocalized electrons make the molecule more stable, and they're used in metallic bonding, which enables electricity and electronics to work. They're used in the aromatics industry to produce styrene, cumene, alkylbenzene, and cyclohexene. Thank you. Bye.